right. Hi, everyone. Thanks for being here today for the Theory of Computing for Fairness seminar series. So today our speaker is Daniel Freund. Daniel is an assistant professor of operations management at MIT Sloan. Before joining MIT, he got his PhD from Cornell, and he was a postdoc at Lyft. His research at a high level, so he's working on like market design, stochastic modeling, and optimization, and he's applying those techniques to problems in transportation, in online platforms, in revenue management, and like many others. And so today, Daniel is actually going to tell us about his recent work on group fairness in dynamic refugee assignments. And so, yeah, Daniel, it's all you now.
Thank you. And thank you all for taking the time. This work is really about a problem that arises in the refugee resettlement pipeline. And in particular, clicker is already not working. All right. And in particular, the goal is to identify what host locations to assign individual refugees to. Before I get to the specific algorithmic or computational question, let me start by talking a little bit about the pipeline. So we have refugees and asylum seekers that arrive to a given host location, in this picture here, the US. And then we have government or non-governmental resettlement agencies that make a decision about which host location should take in the refugee or the asylum seeker. So in the US in particular, the refugee case is allocated to a resettlement agency. There are 11 of those. Those are non-governmental. And the resettlement agency has local affiliates in all sorts of different cities. And those local affiliates are supposed to help the refugee to integrate in the local community, finding housing, finding employment. The case comes with all sorts of data, covariates that characterize the involved individual, age, education level, country of origin, and so forth. And employment at the end is usually measured as a proxy for integration. So in the US, if we want to know whether or not integration of a refugee has been successful or not, we would look at whether or not that person has found employment within 90 days upon arrival. In the Netherlands, that metric is within 2 years upon arrival. There's a lot to discuss about whether or not this is a good proxy. There are some people who strongly believe it is, but it is the proxy that we will use. And one thing that turns out to be true is that the probability of employment for any given refugee heavily depends on the compatibility between this individual person or this individual family and the host location that they are assigned to. So this question of how to assign is the question we will focus on. Mathematically, we can view this dynamic refugee assignment problem as follows. We have T time periods. Each time period corresponds to one case arriving, one refugee arriving. And when the case arrives, they arrive with some set of covariates. Status quo in terms of, as we think about prior to optimization being introduced here, status quo heuristics would not really take into account these covariates and make an assignment potentially random or just by capacity balancing. So in particular, in Switzerland, it's legally mandated that refugees be assigned proportionally to different cantons, to different states. So the easiest way to do that is just to go round robin without any attention to the covariates. The resettlement agency, however, can choose a location, we will denote it J of T, for the case, with the caveat that each location has a pre-specified capacity, Sj. So there might be one location that is really great, but you cannot send everybody to this one location. So when a case T is assigned to a location J of T, that location J of T needs to have capacity remaining. And in the end, we said that the proxy we consider is employment. So in the end, there's a reward if the case gets employed within a certain time period. Now, recently, there's been some work that tries to introduce optimization to this problem of interest. And those optimization-based approaches sort of work in two stages, where the first, they try to estimate the probability of employment for each case in each location. So now, rather than having just a case T with covariates, given those estimates, we have a probability of employment WTJ for each case T in each location J. And the goal is to maximize the expected number of employed cases. If we treat these models as truly giving us the correct probability of a case finding employment, then instead of wondering about the reward if the case gets employed in a given time period, which if you think about the Netherlands would require us to wait for 2 years before we know whether or not we collect the reward, we can just think about the reward as the instantaneous reward that we get based on the estimates that the model has already given us. Now, these optimization approaches are really marvelous in some ways. They show that in predicted employment rate, the improvement of refugee employment could be of a size of roughly 50% in average predicted employment rate across all refugees. So given that refugees are a vulnerable population for whom we really want to ensure positive outcomes or better outcomes, the idea of improving employment by this much obviously is incredibly appealing. At the same time, and this is where our work comes in, there are certain group fairness concerns associated with such an optimization. And in order to explain these, let me give you this very simple example in which refugees arrive from 2 different countries, from pink land and from orange country. And there are 2 locations that we could assign these refugees to, all of whom are perfectly homogeneous within each country. Cambridge and Ithaca. Now, all the cases from pink land only have a probability of 0.1 of finding employment in Cambridge. And everybody, regardless of being from pink land or orange country, has a probability of 0.9 of finding employment in Ithaca. Now, because orange country cases have a probability of 0.2 if we send them to Cambridge, which is higher than the probability of pink land cases in Cambridge, if we were to just optimize, we would get an employment maximizing assignment that assigns all cases from pink land to Ithaca because their per case reward there is 0.9 instead of 0.1. If we assign cases from orange country to Cambridge, we have a per case reward of 0.2 instead of 0.9. The marginal difference is a little bit bigger. Well, it's 0.1 bigger for pink land cases to go to Ithaca than for orange country cases to go to Ithaca. And that difference leads us to a solution where everybody from pink land gets the great deal of being in Ithaca. You can tell that 2 of the authors of this paper got their PhDs at Cornell and really enjoyed their time there. And all of the cases from orange country are stuck in Cambridge with a much lower employment probability. Now, one driving motivation that has really been a focus of our work throughout is that we don't really want to define fairness in this work. But in particular, we also don't want to define group fairness. If we think about country of origin here as groups, but for any definition of fairness that could be binding, it seems like this solution would be unfair because the pink land cases get all of the good capacity and the orange country cases get none of the good capacity. So anything that purely optimizes will necessarily disadvantage these people from orange country. Now, there are different ways in which one could incorporate fairness. In order to do so, one needs to define some fairness criterion. And again, we don't really want to set the fairness criterion because we think that should be done by policymakers who actually study ethics. One simple criterion would be motivated by the idea of do no harm. If you think, for example, about medical interventions, each group should be as good under the optimization on average as they would be under the status quo prior to optimization on average. So the expected value that a group receives in terms of their expected employment value should be at least the expected value of random assignment. So in this case here, we would optimize and we would find, we would randomly assign and we would find, well, for Pinkland, the per case reward is 0.5 if we randomly assign. For orange country, if we randomly assign, the average reward is 0.55. And then we could say, well, our fairness definition could be to say, you can do whatever you want, but each group should not receive a worse outcome than this per case reward that they would receive under a random allocation. Now, in this example, any orange country case that gets assigned to Ithaca benefits the group, but harms the global objective. So satisfying this do no harm condition is in direct conflict with optimization. So this suggests that in this example, at least, you really have an immediate trade-off being, do you want to optimize or do you want fairness? And the more you optimize, the less fairness you get. The more fairness you get, the less you can optimize. That's, of course, not true in general. So consider this example where we have 3 different locations, New York, Cambridge, and Ithaca. The employment probabilities are a little bit different. You still have cases from Pinkland and Orange Country. If we look at the employment maximizing assignment, we again find that the Pinkland cases get all of the good capacity, all of the Ithaca capacity, and half of the Cambridge capacity. And the Orange Country cases get all of the New York capacity, where they have 0 chance of employment, and half of the Cambridge capacity. For global reward, the total expected number of people that find employment would be 96. However, in this setting, if we compute the random assignment for each group, and we then optimize subject to the constraint that this holds true, we actually find that the global reward that we would get is only a little bit smaller. It's 94.71. So we can, in this scenario, almost recover the employment maximizing assignment while respecting this do no harm fairness criterion. Again, as I mentioned before, our goal here is not to prescribe a particular fairness criterion. Instead, we are trying to derive a framework where a policymaker gives us a group fairness criterion that is based on minimum requirements meaning what is the average employment for each group that the group should achieve at least. And the reason I say at least is because it's a minimum. Those requirements should be based on an offline problem that should be feasible, but they can be induced by simple rules. So what do I mean by simple rules? Random assignment is something a policymaker understands. And as we're not imposing the fairness rule, we're really trying to create a setup where the decision is made by this policymaker, and we just want to give algorithms that will work for any such fairness rule that is given. Now, the cost inefficiency that you already saw from the two examples may or may not be small. In the first example, the cost inefficiency was quite large. In the second example, the cost inefficiency was quite small. Now, there are different such rules you can think of. The first one is the do no harm we've discussed before. The second one, very common rule in fairness, would be max min. So we want to ensure that whatever we do globally in terms of how we assign refugee cases, it should be the case that the minimum average outcome for any group is as large as possible. Or another option would be something that we call proportionally optimized, which is motivated by some work in learning, in online learning that has come before us, where we want to think of it as if a group consists, if the number of cases of a particular group, for example, is half of the number of all cases, then we want to solve an optimization problem where that group receives half of the capacity in each location. That's what we call the fair share of capacity in each location. And we optimally assign based on this proportional share of the capacity. And with this, but that is not the assignment that we use. Instead, we use that value as the minimum requirement for that group. So this is just 3 possible rules that you could think of that are at least somewhat reasonably motivated as fairness constraints that a policymaker could choose. We allow in the paper really a much broader set of rules, and there's a particular set of technical conditions they need to fulfill, which are quite reasonable. They effectively say, if your fairness condition requires that everybody gets everything, that's not feasible, so that's not allowed. But anything that is feasible, effectively, we can work with. And the question we want to ask is, for a given fairness rule that gives us the minimum group requirements, how can we dynamically maximize the global employment subject to each group meeting the minimum employment requirement that is given by the fairness rule? So overall, our results can then be summarized as follows. We provide such a flexible framework. We provide algorithms that have asymptotically vanishing regret guarantees, and I'll define in a few slides what that means. And we show using data from partner organizations that enforcing these fairness rules is not costly in the global outcomes in practice. So going back to the 2 examples that I showed initially, when the first example, adding the fairness constraint or the group fairness constraint was quite costly in terms of there was a direct trade-off between either you optimize or you have fairness, we show on data that in practice that is not the case. You can have your cake and eat it too. You can enforce group fairness with a relatively small price in global efficiency. Now, before we get to this, let me just highlight on data where we're coming from in terms of motivation. So when we started this project, the first question we asked ourselves is, well, if you look at the data, is there actually any concern about group fairness? Or maybe the optimization actually does so well that there's no issue with fairness anyway. So we defined a metric that we call the fairness ratio. And the way to think about it is that we look at the minimum over all groups and we compare the realized expected employment score per case for each group so minimum over all groups, the expected employment score per case for the group, divided by the minimum requirement that the fairness rule gives us. On this slide, you see 3 columns: max, min, proportionally optimized, and random. Those are the 3 fairness rules that I previously told you about. And on the in the rows, you see 3 different data sets effectively. 2 are from the Netherlands. The first one defines groups by age bracket, the second one by education level, and the third one comes from the US and defines groups by country of origin. Now, you see 2 different methods of assigning people right now. The first one is random. The second one is the offline optimum that just maximizes the refugees' employment. And what you can tell is that in many cases, the optimal assignment, but even more so the random assignment, does very poorly relative to meeting these minimum requirements. So in the bottom left, for example, you see that the random allocation in the US with groups defined by country of origin gives at least one group less than a quarter of the employment outcomes that that group should be getting. But then you also find, for example, in the top right, that in the Netherlands, if we define groups by age bracket, the optimal solution, which doesn't take fairness constraints into account, just implicitly fulfills the do no harm condition for every group. So that is the motivation for our work. This actually got picked up recently by an op-ed in Bloomberg Law. Reading the op-ed, I want to highlight that we don't have legal expertise. So the author of the op-ed quoted us in various parts with respect to our legal expertise. And I want to emphasize that we were trying to read regulations and we are trying to understand things. So I don't think that one should take too literally the issues we raise when we say that the use of the algorithms may be jeopardized by such fairness issues. That's our understanding of the regulations, but we are not the lawyers. But also, and that's what I want to get to in a second, the positive part of our results is that we provide algorithms that can fulfill group fairness guarantees. And in that regard, we're certainly not trying to argue in the paper that algorithms should not be used in refugee resettlement. In fact, going back to the earlier slide, going back to the idea that one can increase employment outcomes for refugees by 50%, I think it would be tragic if such improvements were not realized. We really want those improvements to be realized. What our work shows is that the price of incorporating some group fairness criteria on top of that is relatively small, and the benefit remains therefore very, very large. Okay, let's formalize things. We have in our model that the distribution of case covariates is IID. So we have a model, a machine learning model that is given that will map the covariates to location weights. The location weights is the employment probability of case T in location J. And we assume that there are these ex post minimum requirements, OG, for every group G. What do I mean by ex post minimum requirements? Those are the requirements for each group G. OG shall be the minimum average, shall be a lower bound on the average employment of cases from group G. And we're given capacity for each location J, and that's denoted as J. And then as our cases arrive sequentially, each group case has a group membership, GT. and those location weights, the resettlement agency assigns to a non-empty location J of t, non-empty meaning there's capacity remaining, and thereby depletes one capacity from that location. And then a reward is earned based on the location that the case has been assigned to. With this formulation, we can write an offline problem which effectively says maximize over all assignments the average employment outcome across all of the cases, subject to, now there are three types of constraints. The bottom left constraint says every case needs to be assigned. The bottom right constraint says if you look at any location, the number of cases assigned need to respect the capacity. And this constraint, the big one in the middle, that one says if you look at the average outcome for any group, meaning if you look at all the cases of a given group and look at what is their employment all combined, that shall be at least what the fairness rule dictates for the group. And with this being defined, we can then define what we mean by regret. What we mean by regret are the following two things. On the one hand, we want to be as close as possible to this value O star. So we define our global regret as what is the average across all cases of employment compared to this O star value. And we define, for each group G, what we call the G regret, which is what is the average employment outcome for this group relative to, and this is now a little bit non-standard, the minimum of OG, OG being what is given ex post as a minimum requirement, and the expectation of OG. Now you might ask, why do we take this minimum if we set it's ex post? Well, if we just look at the expectation, that is sort of a fair comparison. There are some recent works that look at the true optimum rather than the expected optimum. The expected optimum is an upper bound on the true optimum, so that one is reasonable. For the group G regret, comparing just to expectation of OG would be too difficult, because you might have a particular group G that has too few arrivals that have high employment probabilities, no matter where they get assigned to. So if you compare to the expectation, you wouldn't be able to get strong results. And comparing to the true optimum is also in general too difficult. What do I mean in general? That depends on the fairness rule. So under the max-min fairness rule, we show a pretty convincing, we find, impossibility result in order to, when trying to compare to this OG. At the same time, for well-behaved fairness rules that fulfill a particular regularity condition, we show that we can actually have vanishing regret with respect to just OG, which we refer to as the ex post regret. I will not focus on that detail in the rest of the talk. Instead, I will focus on the benchmarks that we have here, which is either the global regret or the group G regret. Now, the first natural thing that you might think of doing, if you have an ML model that tells you for each case the probability that they will find employment in a given location, is to just assign them greedily. That would make use at least of the machine learning model. The downside of that, of course, is that if there's a particular location that is a very valuable location for all cases, that will run out of capacity very fast. So this does not account for the capacities, and thereby uses valuable locations very inefficiently early on. Existing work has used what has been referred to in the revenue management literature as bit prices. In approximation algorithms, we would just call them dual values, or in linear programming, in order to identify the opportunity cost of a particular location. And then rather than assigning to the location that has the highest employment probability, we normalize the employment probability at each location with this opportunity cost. And what one can show is that this will do quite well at imitating the optimum solution. Now, of course, in order to do that, you'll need to take some Lagrangian, you'll need to compute these opportunity costs. But once you have that, you can implement such an algorithm. And the only downside is it still does not account for group fairness. So right now, it only has the opportunity cost of the locations. And if we try this on data, we find that in terms of group fairness, unsurprisingly, it does roughly like the offline optimum. So the good news is we can reasonably, under the assumptions that we make, imitate the offline optimum. The bad news, of course, is the offline optimum was already unfair. So now the question is, can we somehow adapt such an algorithm to not just imitate the to not just imitate the offline optimum, but instead to imitate the offline optimum that respects the group fairness constraints? And the answer is yes, we can, by instead Lagrangifying the fairness-based offline problem, or the expectation thereof. And that gives us what we call the amplified bit price control. So if we take the Lagrangian of this problem here, which has the fairness constraints included, then rather than just having the weight or the employment score of a case at a location minus mu j star, this WTJ now gets amplified through this group-specific multiplier. And what we can show is that by adapting the opportunity, by adapting the opportunity cost sort of through this amplifier, we now get a new algorithm. And following those choices, following in each iteration the location that maximizes this, up to the point where at some point locations get depleted, at which point one can just assign arbitrarily or in a load balancing manner. Such an assignment will actually give us both global regret and group G regret guarantees that work very well when T is very large. The main proof idea is that until we are depleted, we perform very well in every period in expectation, and we don't deplete until rather late in the horizon. So everything that I've done so far is pretty straightforward and sort of what one would usually do in problems of this type. The problem with this solution is that it involves this term here, which is the square root of 1 over the probability of a case being of a particular group. So why is that a problem? Well, if you think about defining cases by education level, then, defining groups by education level, then each group is going to be fairly large. There are only like 6 different education levels in the classification in the Netherlands. So you're not going to have a problem with some group just having 5 arrivals. But if you define groups based on country of origin, you might have groups that are quite large. And if a group is large, this square root term is not vanishingly small like we would want it to be. So this guarantee ends up being vacuous for groups that are small. And in fact, if we now run this algorithm on data, we find what we would have expected based on this observation. In the Netherlands, where groups are defined by age or education level and are thus quite large, the algorithm does always quite well in terms of fulfilling the group fairness minimum requirements. In the US, where groups could be a lot smaller, it's a mixed bag, right? It's definitely better than the other methods we've seen so far, than randomly assigning or than the bid price control that does not have any group accommodations, fairness, that does not take into account fairness considerations. But it's not exactly good. So, for example, in the bottom left, we're still, for some group, almost a factor 2 away from where the group should be. Or in this column here, we're still a factor 4/3 almost away from where the group should be. Now, what is the roadblock? What is causing this? There are really 2 issues. One is, if we think about the expected score of an assignment, that is above the minimum requirement, but this concentration happens at a rate that is sort of inverse to their size. Think of central limit theorem. You're off by some square root in the number of samples. If a group is small, you just don't have that many samples. And the second is, if you have a small group and most of the arrivals of that group occur after capacities in valuable locations are all depleted, then we cannot even act based on the amplified bid price. So we would really like to have an algorithm that sort of has it all. We would like to have an algorithm that works like the amplified bid price, but solves this issue here. We derive such an algorithm, which we call the conservative bid price control, by sort of adding just 2 small pieces to the amplified bid price. One is, at each location, we will distinguish between free and reserve capacities for each group and each location. And the way to think about it is that most of the capacity will be free capacity, but there will be some reserve capacity. And the second will be that we introduce what we call a predict to meet condition. And the way to think about that is that we will ask for a given arrival of a given group membership. Would we meet the group requirement for this group if we followed the amplified bid price control now, but then in the future, for the rest of the horizon, we will always assign greedily? Now, of course, we don't know that because we don't know the future arrivals, but we can add some buffers to capture randomness in the future arrivals. So with these 2 ideas, the conservative bid price control proceeds as follows. It observes an arrival of some case of a given group, and it looks at whether or not this predict to meet condition is satisfied. If it's satisfied, meaning if we predict that we could start tomorrow assigning people greedily, and just for the rest of today, we can assign based on the amplified bid price control, then we would like to just follow the amplified bid price. So if there is free capacity at the location chosen by the amplified bit price control, then we follow the amplified bit price control, else we just assign arbitrarily. If this condition is not satisfied, then we would like to assign the current case greedily in order to get closer to the point where we believe that this group might still meet its minimum requirement. So the way to think about this truly is that we are complementing our amplified bit price control through greedy steps that will only be used if we are at a risk, or if we predict that we're at a serious risk to not meet the minimum requirements for the group. And then if we find that the free capacity actually is also exhausted at the greedy location, then that is where the reserve capacity comes in, and we ask, is there reserve capacity for this group at this location? If yes, we can still assign greedily, else we assign arbitrarily. And those greedy steps complementing the base algorithm allow us to provide theoretical guarantees that with high probability bound both our global and our group regret in a way that no longer depends on the group size. That is what we wanted. There's one assumption baked in here, which is there's now an epsilon in the guarantee, and epsilon captures a lower bound on the expected benefit of a greedy assignment. So we're trying in this algorithm to sort of complement the amplified bit price control through greedy assignments for a given group, or for any group. It should be the case that getting assignments greedily should somehow help. And that is what this condition this lower bound tries to capture. Now, there are two aspects of this guarantee. Compared to the previous one, the positive one is we don't have the dependence on the group size. The negative one is we now have dependence in both the group regret and the global regret on the number of groups. And we also have the dependence of epsilon. And to be intellectually honest, we also need to recognize the high probability statement only holds for t that is much larger than what is needed in the previous statement, and then is much larger than occurs in practice. So the t that we require for those theoretical guarantees to hold is of order 1 million, whereas in practice we would expect to observe thousands of cases. Nonetheless, when we actually try the algorithm on data, we find that it exactly resolves the issue that we previously observed with the amplified bit price control, which is that even in cases where the groups are small, remember the bottom column, the US, groups are defined by country of origin, and we have some countries of origin from where only a handful of cases maybe arrive. There, we're now across the board either at 100%, meaning we're actually meeting the target, or we're only just below. So in that regard, we're doing much better. Everything that I've said throughout this talk has been focused on the fairness, and I haven't really told you anything about the global efficiency in the data. So let me get to that now. In this table, I'm showing you 5 different possible assignments, and I'm comparing them all to an offline optimum that assigns all cases with no fairness constraints. The bottom one here is the offline method that assigns all cases with the fairness constraints. The second one is the bid price control that assigns all cases in an online manner, but without incorporating fairness constraints. Then you have the amplified bid price control and the conservative bid price control, the two algorithms I've described. And then you have a random assignment. And again, all of these numbers are the ratio of the global employment, the combined average employment of all cases, relative to what the offline optimum achieves. Now, the first number we want to look at is, well, how poorly does the random assignment do? And clearly it's very, very bad. It's less than 50% in the Netherlands, 2/3 in the US. The bid price control that does not take into account fairness constraints, that just tries to imitate opt, does pretty well, loses at most 2%. If we look at our two algorithms, we see that we lose a little bit relative to the bid price control. At most 3% here. At the same time, we do get with these algorithms a much better performance with respect to the group fairness, as we saw on the previous slide. So across the board, we see that CBP and ABP, if we care about those group fairness constraints, provide a much better trade-off than either not optimizing or optimizing without the fairness considerations. All the figures that I've shown so far considered IID arrivals where we've also proven our theorems. If we instead use real data where we cannot sample in order to obtain, for example, the Lagrange multipliers, but we just need to sample based on previous historical data, our performance doesn't look as good anymore. But except for the US max-min case in the bottom left, it still looks relatively good. We're still observing a much better performance with respect to fairness, while at the same time losing only a few percent relative to the bid price that would not be incorporating the fairness constraints. So in summary, the refugee pipeline is clearly an important societal problem that needs optimization. Such optimization has a real risk of creating disparate outcomes across different population groups. What we show is that there are algorithms that perform well with respect to given fairness rules. Of course, this requires a fairness rule to be given by the policymaker. We want to stay far away from making the decision of what that fairness rule should be. Our algorithms have asymptotically vanishing regret guarantees under IID assumptions and so forth. And maybe not most importantly, but very importantly to me at least, we find that the incorporating those fairness constraints does not cost us too much in global performance. I would have felt very bad if the outcome of this research had been that you really have to choose, as in the pink and orange country example, between either you get better outcomes overall or you get group fairness. It turns out on the data that we have that you seem to be able to have both. There are various extensions that would be interesting, but maybe I'll leave the last 4 minutes for questions.
Yeah, thanks a lot, Daniel, for the great talk. So yeah, we have time maybe for like 1 or 2 questions right now, but we should try to wrap up at like 1 p.m. So if you guys have any questions, please go ahead. see that someone is connecting to audio, trying to give a... Amanda, are you trying to ask a question?
I don't think so. I think it went on and off throughout the talk to the extent I could observe it. All right, I'll just say 2 words maybe then on the possible extensions, because I think that there are interesting questions. They are not so much with respect to algorithms, but even just with respect to how to model it, which I think should be of interest to this group. In the refugee setting that we're in, each case is not just one person. It's potentially a family. And the assignment of a case needs to be to one place. You cannot say father and son go to one location, mother and daughter go to another location. But you do have intersectional groups. You may have a family where one part comes from one country of origin, another comes from another. Even more obvious with age and educational level. So how to define, the way we're defining these right now are effectively based on who filled out paperwork, but how to define group membership is actually not even clear. And in a similar sense, if you have families then with, sorry, that is really the second point, which is family with group heterogeneous members. You might have a family where there's a father and a mother. If you define groups by gender, it's really, it has both. And with respect to intersectional groups, you may not just care about country of origin and education level, you might care about intersections between those two. And for those, it turns out that even just defining any of the fairness rules we've considered explicitly becomes a little bit non-trivial. So there, before one even can think about designing algorithms, I think it would be interesting to consider how to even model those aspects.
Also, like a very, very good question. But like you mentioned earlier in the talk, kind of like potential issues like privacy regulations and everything, and you said like, I mean, that you were trying to read them like, as best as possible, but like you're not an expert, and I feel like none of us here are an expert. Do you have like actually a path to kind of like understand this better? I'm actually generally interested in like the extent to which stuff like this can be implemented given like privacy practices, for example, GDPR.
So one thing I can say is that these things are being implemented. So maybe I should have been clearer about that.
Okay.
So there are various pilots, both in the US and in Europe, that are actually trying to implement the optimization. And GeoMatch, in particular, out of Stanford, is an organization trying to do exactly that. Elizabeth, one of our co-authors, has an affiliation with GeoMatch, and we are trying to sort of shield against any such issues arising. The extent, I think, to which the legal issues arise with this, much more than with privacy issues, maybe occurs a little bit due to also a lack of understanding, right? Because we are, for example, we're treating the machine learning model that predicts employment as given. We're interested in the allocation decision that comes thereafter. That is, in a sense, not the decision that people usually tend to worry about. If we're thinking about fairness in AI, usually we're thinking about, is the machine learning model fair?
Yeah. I see. So okay, so just and just like to bounce off of this. Sorry, now I'm keeping everyone here, but like if you guys need to leave, please go. Yeah. So basically, also like from what I'm reading at the moment right now. So like the point, and like from what you said, like the point you're talking about is like a point about fairness, and like GDPR here is requiring people to prevent those kind of discriminatory effects. To what? But GDPR also actually requires you to protect privacy in some to some extent. Do we understand to what extent those are kind of like incompatible? This is not a question about your work anymore. This is a question about GDPR, I guess. But yeah,
Um, so there's I guess, I don't, again, I'm not an expert on the GDPR requirements. I know that privacy of various types, privacy guarantees of various types are guaranteed by GDPR. I'm not exactly sure what that would mean here, in the sense
right.
of,
I feel like there's
if
potentially
I'm
a
a, if
tension,
I'm
right?
like,
Yeah,
if you think of a government organization that collects data of asylum seekers or refugees arriving to the country, that seems like something that even in GDPR you would assume that a country is supposed to have public records.
I would hope so. Yeah,
Yes.
like kind of like the reason this question was coming up, for example, was you would imagine this is absolutely natural thing to do, like you want to collect that data, especially like if you want to do refugee assignment, right? But there's always other situations, for example, in the US, where you're supposed to like you can help with like fairness and discrimination by collecting data about people, like university
Yes.
admissions, and where we have just been told we're not allowed to use university, like we're not allowed to collect this data and use like race and everything, for example, university admissions, which is why like I'm bringing this up because it's
Yes.
a bit worrying to me.
I do think that, I mean, if you think about the amplifier in our algorithm,
Yeah,
you could view that as a way of implementing an advantage for a group over another in order to meet the fairness constraints that have been set.
right.
At the same time, I want to say, I do want to stay away from the actual policy question.
Fair. Yeah.
I realize that that's lazy on my part, but the policymaker can define the fairness rule.
Yeah, and that's like that was part of like a big point. Like that was a big point of your talk too, right? That like you're kind of like trying to accommodate like whatever kind of like fairness definition we have in there. So yeah, that makes a lot of sense.
Let me maybe add just 2 cents to that. If you think about the policymaker as having choices, the policymaker can say, we do not want to use data, we go with random assignment.
Yeah,
I think the data shows that that would be a really poor outcome.
right.
As a citizen, I don't like that.
Yeah,
They can say, okay, let's just optimize with no consideration of fairness. And that has group fairness concerns, as the data shows. If the policymaker says, I don't care, that's up to them. If they do care, then I would say at least we provide them a way of addressing these. But it's a delicate balance between those three
yeah,
options and how to interpolate between any two.
that makes a lot of sense. Yeah, yeah. I guess, well, you know, it's actually like 1:06 right now, so I should probably let everyone go and like we should probably end things here. But like I want to thank you again, Danielle, for the great talk. Yeah, I'll see everyone soon. See everyone here next week. Bye,
Thank you
everyone.
very much. Bye.